welcome to the deep dive. All right, get ready because today we are going subatomic.
Oh, sounds exciting.
We are diving into the world of the weak force.
Ooh.
Now, you've heard of the strong force, gravity, electromagnetism.
Right, the fundamental forces.
Right, but this one, this weak force, it's kind of mysterious, but just as crucial.
Yeah, it's definitely a bit of an underdog.
It really is. So what we are going to do is figure out what makes this thing tick.
Yeah, unlock its secrets.
Exactly. So before we get into the nitty-gritty, let's set the stage.
Okay, sounds good.
The weak force. What is? Give me the elevator pitch.
Well, think about it this way. It's the force behind radioactive decay.
Oh, okay.
The reason why unstable atoms transform into more stable ones.
So it's kind of like nature's recycling program then,
Exactly.
breaking things down
Yeah, at the atomic level.
at the tiniest level. And what's amazing is that it all happens over such incredibly tiny distances.
It does. Yeah, we're talking like 10 to the power of negative 18 meters.
Whoa,
A millionth of a billionth of a meter.
that is mind-bogglingly small.
It is.
So it's a force that works at close range, but it's responsible for these huge transformations.
It is.
Yeah, I mean, come on.
And here's another surprise.
Okay.
Even though it's called the weak force,
Right.
it's actually stronger than gravity at the subatomic scale.
Right.
Yeah, gravity might rule the cosmos, but in the quantum world, the weak force is a major player.
Wow, so we've got this powerful force operating over minuscule distances, shaping the building blocks of matter.
Yeah.
And now it's time to introduce the characters that make it all happen, the W and Z bosons.
Ah, yes.
What makes these particles so special?
Well, think of them as like specialized delivery trucks,
Right.
transporting packages of energy and momentum.
Right.
And when those packages are delivered, they can actually cause particles to transform.
Okay, so they're not just messengers, they're like agents of change.
Exactly, yeah.
And we've got three different types of these bosons, right?
Yes.
We've got the W plus, W minus, and Z.
Mm-hmm.
What sets them apart?
So the W bosons, they carry an electric charge,
Yeah.
positive for the W plus and negative for the W minus.
Right.
And they're heavy. Each one has a mass about 80 times greater than a proton.
Wow, these are some seriously hefty particles.
They are, yeah.
And what about the Z boson?
So the Z boson is electrically neutral,
Okay.
and it's even heavier than the W bosons, clocking in at about 91 times the mass of a proton.
Wow. Okay, so these are no lightweight messengers.
No.
But how do we even figure out that these particles existed in the first place? Were they always part of the picture, or was this a shocking discovery?
Well, their story is really a testament to the power of theoretical physics
Okay.
back in the 1960s.
Okay.
The idea of W and Z bosons was just a theoretical prediction.
Mhm.
Physicists were working on this theory called the electroweak theory.
Electroweak theory. That sounds like a mouthful.
It is a bit of a mouthful,
Yeah.
but the idea is incredibly elegant.
Okay.
It says that the weak force and electromagnetism, which seems so different at the everyday level, are actually two sides of the same coin. They're unified at very high energies.
So it's like realizing that two seemingly separate things are actually connected at a deeper level.
Exactly. Yeah, like discovering that two rivers actually spring from the same source.
Yes. Okay, I like that.
And the architects of this theory, Sheldon Glashow, Abdus Salam, and Steven Weinberg,
Right.
they predicted the existence of these W and Z bosons as the carriers of this unified electroweak force.
So they basically said, hey, if our theory's right, this has to exist.
Exactly, yeah. These particles must exist.
And they were right. They eventually won the Nobel Prize in physics for their work.
They did, yeah, well deserved.
Absolutely. But there's a difference between a theory and experimental proof, right?
There is.
So the world had to wait until the 1980s for confirmation that these particles were real.
Yeah, quite a wait.
So the hunt was on. How did they finally find these elusive particles?
Well, it took some of the most powerful particle accelerators ever built.
Oh, wow.
Scientists at CERN, the European Organization for Nuclear Research,
Right.
they used a machine called the superproton synchrotron to smash protons together
Okay.
at incredibly high energies.
So these high energy collisions, they created the W and Z bosons.
Yes.
So sort of like recreating the conditions of the early universe in the lab.
Yeah, that's a great way to put it.
Wow.
The energy released in these collisions was enough to briefly create these heavy bosons.
Right.
And their signatures were captured by the detectors.
It must have been an amazing moment to finally see that evidence of these particles that had been predicted decades earlier.
It was a huge triumph.
It really solidified our understanding of the electroweak theory.
Absolutely.
But, okay, we've got these particles, these messengers of the weak force, but what does that actually look like in action? How do they shape the universe around us?
Well, that's where it gets really interesting.
Okay,
The W and Z bosons mediate different types of weak interactions.
okay.
You can think of it as like two different delivery services, each with their own specialty.
I'm intrigued. Tell me more about these delivery services.
Okay, so first you've got the W bosons,
Hmm.
and they're the stars of what we call charged current interactions.
Charged current interactions.
Yeah, these interactions involve the exchange of electric charge.
Oh, okay.
So imagine a particle with a negative charge suddenly becoming positive.
Wow.
That's the kind of transformation the W bosons can mediate.
So they're like subatomic electricians rewiring the charges of particles.
Yeah, that's a great analogy.
So what kind of processes are we talking about here?
Well, the most famous example is probably beta decay,
Beta decay.
the process that makes radioactive elements, well, radioactive.
So this is where things get dangerous, right?
Well, not always.
Okay.
Beta decay is actually happening all around us, even in our own bodies.
Oh, really?
Yeah, and it's used in all sorts of applications, from medical treatments to archaeological dating.
Hmm.
But the key is that it involves the weak force, specifically the W bosons.
So walk me through this. How does a W boson cause beta decay?
Okay, let's take beta minus decay as an example.
Okay.
Imagine a neutron sitting inside an atomic nucleus.
Yeah.
It's a neutral particle, no electric charge.
Right.
But suddenly, this neutron decides to transform into a proton, which has a positive charge.
Okay.
To do this, it emits a W minus boson, which carries away the negative charge.
Correct.
And this W minus boson then decays into an electron and an antineutrino.
Whoa.
So you started with a neutron and you end up with a proton, an electron, and an antineutrino, all thanks to the W boson.
So the W boson is like the facilitator,
Yeah.
making this whole transformation possible.
Exactly.
Wow, it's kind of mind-boggling how a single particle can orchestrate such a complex process.
Yeah, it's pretty amazing.
But what about the opposite? Can a proton become a neutron?
Absolutely. That's called beta plus decay or positron emission.
Okay.
In this case, a proton inside the nucleus transforms into a neutron.
Right.
But to do this, it has to get rid of its positive charge.
Mm-hmm.
And that's where the W plus boson comes in.
Okay.
The proton emits a W plus boson.
Which decays into a positron, the antimatter counterpart of an electron,
Wow.
and a neutrino.
Okay, so the W bosons are like the ultimate shapeshifters,
Yeah.
enabling these back and forth transformations between protons and neutrons.
They are, yeah.
But we also have the Z boson. What kind of delivery service does it provide?
Okay, so the Z boson is all about neutral current interactions.
Neutral current.
Yeah, these interactions don't involve a change in electric charge.
Mm.
It's like a subtle nudge rather than a complete rewiring.
So if the W bosons are electricians, is the Z boson more like, I don't know, a gentle massage therapist?
Haha, maybe not a massage therapist, but yeah, you're getting the idea.
Okay.
It's a subtler interaction.
Okay.
A good example is neutrino scattering, where a neutrino interacts with another particle, like an electron.
Neutrinos, those are those ghostly particles that are almost impossible to detect.
Exactly, incredibly tiny,
Right.
and barely interact with anything.
Right.
But when a neutrino does interact, it's often via the weak force, mediated by the Z boson.
Okay.
So the neutrino and the other particle, they exchange a Z boson,
Mm.
and this changes their momentum and energy, but their electric charge remains the same.
So it's like a subatomic billiards game. The particles collide and bounce off each other, but there's no exchange of charge.
Yeah, that's a good way to visualize it.
Okay, but wait. I thought neutrinos were supposed to be massless. How do they even interact with the Z boson if they have no mass?
Ah, that's a great question.
Yeah.
And it leads us to another fascinating aspect of the weak force, the Higgs mechanism.
Okay.
It turns out that the W and Z bosons, as well as some other particles, get their mass from interacting with something called the Higgs field.
At Higgs field. This is getting even more intriguing.
Yeah, it's a pretty wild concept.
So what is this Higgs field and how does it give particles mass?
Well, imagine a field that permeates all of space,
Okay.
kind of like an invisible ocean.
Right.
This is the Higgs field.
Yeah.
And just like objects moving through water experience resistance.
Particles moving through the Higgs field experience resistance as well.
Okay.
And this resistance is what we perceive as mass.
So the more a particle interacts with the Higgs field, the more massive it becomes?
Exactly.
Okay,
And the W and Z bosons interact very strongly with the Higgs field, which is why they have such large masses.
right.
But the neutrino interacts very weakly with the Higgs field,
Okay.
which means it has a very tiny but non-zero mass.
Okay, so even neutrinos, those elusive particles, they're affected by the Higgs field.
They are, yeah.
And speaking of the Higgs field, there's a particle associated with it, right?
Yes.
The famous Higgs boson.
That's right, the Higgs boson.
Yeah.
The discovery of the Higgs boson back in 2012 was a monumental event in particle physics.
Yeah, I remember that. That was big news.
It was the final piece of the puzzle confirming the existence of the Higgs field
Wow.
and explaining how particles acquire mass.
So we've gone from these theoretical predictions of the W and Z bosons to actually observing them in particle accelerators. And now we've even discovered the Higgs boson, which explains how they get their mass.
It's been quite a journey.
That's an incredible journey, but I'm sure there's more to this story, right? What are some of the implications of these discoveries, and what mysteries are scientists still trying to unravel when it comes to the weak force?
Oh, yeah, the story definitely doesn't end there.
Okay.
The weak force has profound implications for everything from the evolution of stars to the very existence of matter in the universe.
Wow. Okay, so big implications.
Yeah, and there's still so much we don't know.
Well, it sounds like we have a lot more ground to cover. Join us in part 2 of this deep dive as we explore the far-reaching impact of the weak force and delve into some of the remaining mysteries that scientists are working to solve.
Welcome back to our exploration of the weak force. Before we jump back into the W and Z bosons, I'd like to add one more thought about the Higgs mechanism.
Oh, absolutely. Please do. We were just talking about how the Higgs field gives particles their mass and how the discovery of the Higgs boson confirmed its existence.
Right. Well, it's not just about giving particles mass.
Bro.
The Higgs mechanism also plays a role in something called electroweak symmetry breaking,
Electroweak symmetry breaking.
which we touched on earlier.
Right. You mentioned that at high energies, the weak force and electromagnetism are unified into a single electroweak force.
Exactly. But as the universe cooled down after the Big Bang,
Right.
the symmetry broke.
Okay.
The weak force and electromagnetism became distinct forces
Right.
with different properties.
Okay.
And the Higgs mechanism is the reason why this happened.
So the Higgs field is not only responsible for giving particles mass, but it's also the reason why the weak force and electromagnetism went their separate ways.
Yeah, that's a good way to think about it.
That's a pretty big deal.
It is. It's one of the most profound concepts in particle physics.
Okay, that's amazing. Now I'm even more curious to delve deeper into the weak force itself.
Okay.
Before the break, we were starting to talk about some of the unique things about the weak force, like this thing called parity violation.
Right, parity violation.
What's that all about? It sounds kind of mysterious.
It is a bit mysterious.
Yeah.
Parity in physics refers to the idea that the laws of physics should be the same whether you're looking at a system directly
Okay.
or looking at its mirror image.
Okay, so if you have a particle interaction happening in front of a mirror,
Right.
its reflection in the mirror should behave the same way.
Exactly. And for a long time, physicists just assumed that parity was conserved in all fundamental interactions.
Right. Okay.
But then in the 1950s, they made a startling discovery.
Okay.
The weak force doesn't play by the same rules.
Oh.
It violates parity.
So the weak force is like the rebellious teenager of the fundamental forces.
Uh-huh. Yeah, you could say that.
Right.
It was a revolutionary finding.
So what does that mean then? What does that look like?
It means that if you were to observe a weak interaction in a mirror,
Okay.
it wouldn't look exactly the same as the original interaction. It would be flipped, like a left hand becoming a right hand.
Okay, I'm trying to wrap my head around this.
Yeah. It's a tricky concept.
How did they actually figure this out? Do they have, like, tiny mirrors for subatomic particles?
Not quite. The key experiment that proved parity violation was done in 1957
Okay.
by Chanshum Wu and her team.
Okay.
They studied the beta decay of cobalt-60 atoms.
Okay.
They aligned the spins of these atoms using a magnetic field,
Right.
and then they observed the direction in which the electrons were emitted during the decay.
So they were looking at which way the electrons were flying out during this radioactive decay process.
Exactly.
And what did they find?
They found that the electrons were preferentially emitted in one direction relative to the spin of the cobalt-60 nuclei.
So the electrons had a preferred direction.
Yes.
But wouldn't you expect them to fly out in all directions randomly?
That's what physicists thought at the time.
Okay.
If parity were conserved, you would expect a symmetrical distribution.
Right. Okay.
But the fact that the electrons had a preferred direction meant that the mirror image of this decay process
Yeah.
wouldn't look the same. So that's how they knew that parity was being violated.
Exactly.
The weak force was showing a clear preference for one direction over another.
Yes, it was breaking the mirror symmetry.
Okay, that is wild. It really shakes up our intuitive understanding of how the universe works.
It does, yeah.
But what are the implications of this parity violation? Does it affect anything in the grand scheme of things?
It turns out that it does.
Okay.
Parity violation has major implications for our understanding of the universe,
Okay.
particularly for the matter-antimatter asymmetry problem.
The matter-antimatter asymmetry problem.
Yeah.
Remind me what that is again.
Right, so it's one of the biggest mysteries in cosmology.
Yeah.
The Big Bang
Right.
should have created equal amounts of matter and antimatter. But today, the universe is dominated by matter.
Right. Where did all the antimatter go?
Exactly. It's like
Yeah.
the universe had a giant preference for matter over antimatter.
Right.
And you're saying that parity violation might have something to do with this.
Exactly. The violation of parity in certain weak interactions
Okay.
means that matter and antimatter don't behave in perfectly symmetrical ways.
Okay.
And this subtle asymmetry
Yeah.
could have tipped the scales in favor of matter in the early universe, leading to the abundance of matter that we observe today.
Wow, that is mind-blowing. So
Yeah.
this seemingly abstract concept of parity violation could hold the key to solving one of the biggest mysteries of the cosmos.
It could. Yeah.
That's a reminder that even the smallest details in physics can have huge consequences.
Absolutely. It shows how interconnected everything is.
Okay, let's shift gears a bit and talk about another fascinating aspect of the weak force, neutrinos.
Okay, neutrinos.
Earlier, you mentioned that they interact through neutral current interactions,
Right.
mediated by the Z boson.
Yes.
But they're notoriously difficult to detect, right? I mean, trillions of them are passing through us every second.
That's right.
And we don't even notice.
We don't.
So how do scientists even study them?
It's a challenge, for sure. But scientists have come up with some incredibly ingenious ways
Okay.
to detect these elusive particles.
Okay.
They build massive detectors, often located deep underground,
Okay.
to shield them from cosmic rays, which can interfere with the measurement.
So they go deep underground to create a sort of neutrino sanctuary where they can try to catch these particles in action.
Exactly. They need to create these really controlled environments,
Wow.
and they have to be patient.
I bet.
Neutrinos interact so rarely that you need a lot of material in the detector,
Right.
and a lot of time to capture even a handful of interactions.
It sounds like trying to find a needle in a haystack, except the haystack is made of solid rock and the needle is almost invisible.
Yeah, it's a pretty good analogy.
Okay. But all this effort must be worth it.
It is.
What have we learned about neutrinos from these experiments?
Well, we've learned some amazing things. One of the most exciting discoveries
Okay.
is that neutrinos can change their flavor.
Neutrinos have flavors, like ice cream.
Not quite. In particle physics, flavor refers to the different types of neutrinos.
Right.
There are 3 flavors:
Okay.
electron neutrinos, muon neutrinos, and tau neutrinos,
Okay.
each associated with a different charged lepton.
Okay, so we have electron neutrinos, muon neutrinos, and tau neutrinos. So what does it mean that they can change their flavor?
It's called neutrino oscillation.
Okay.
As neutrinos travel through space, they can spontaneously transform from one flavor to another. An electron neutrino could become a muon neutrino, and then later it might switch back to an electron neutrino.
Wow.
It's like they have an identity crisis.
That's crazy. So these neutrinos are like shapeshifters, constantly changing their identities as they zip through space.
Yeah, they're pretty slippery characters.
But how is this even possible?
Well, it's only possible because neutrinos have mass.
Right.
If they were massless, they wouldn't be able to oscillate.
Okay.
And guess what force is responsible for these oscillations?
I have a feeling I know the answer. The weak force.
You got it. Neutrino oscillations are driven by the weak force.
Of course.
The neutrinos interact with the W and Z bosons.
Right.
And these interactions can cause them to change their flavor.
It's another example of how the weak force can have subtle but profound effects.
Absolutely.
This is incredible. So these ghostly particles, these masters of disguise, they're giving us clues about the fundamental nature of the weak force.
Yeah, they really are.
But what are the implications of these neutrino oscillations? Why should we care that neutrinos are changing their flavors?
Well, it turns out that neutrino oscillations have some pretty significant implications.
Okay.
First of all, they tell us that neutrinos must have mass,
Okay.
even though it's incredibly tiny.
Right.
And that means our current understanding of particle physics, the standard model,
Right.
is incomplete.
So the standard model, which is supposed to describe all the fundamental particles and forces,
Yeah,
doesn't quite have neutrinos figured out.
right. The standard model initially predicted that neutrinos were massless, but neutrino oscillations prove that they do have mass, albeit a very small one.
Mm.
And that means we need to go beyond the standard model
Right.
to fully understand these particles.
So neutrinos are not just these weird, elusive particles. They're actually pointing us toward a deeper understanding of the universe.
Yeah, they're like little messengers from the unknown.
That's so cool.
Hmm.
And you mentioned that neutrino oscillations have other implications as well.
They do, yes.
Well,
They also have implications for astrophysics and cosmology.
okay.
Neutrinos are produced in a variety of astrophysical processes,
Okay.
from the nuclear fusion in the sun to the explosions of supernovae.
Right.
And understanding how they oscillate is crucial for interpreting the data we get from these distant objects.
So by studying neutrinos, we're not just learning about these tiny particles themselves. We're also learning about the stars, galaxies, and the universe as a whole.
Exactly. It's all connected.
And then there's the fact that neutrinos played a crucial role in the very early universe.
Right. In the first few seconds after the Big Bang.
Okay, now I'm really intrigued. The early universe, that's the time just after the Big Bang, right?
Yes.
What do neutrinos have to do with that?
Well, in the very early universe, everything was incredibly hot and dense.
Right.
It was like a giant cosmic soup of particles, including neutrinos.
Okay.
And these neutrinos interacted frequently with other particles, shaping the evolution of the universe.
So they were more than just passive bystanders. They
Yeah.
were actively shaping the universe.
Yes. For example, they influenced the formation of the first light elements after the Big Bang.
Hmm.
And they also played a role in how the universe expanded and cooled down.
Wow. It's amazing to think that these tiny, ghostly particles had such a profound impact on the universe as we know it.
It is that their influence is really far-reaching.
But I'm sure there's even more to the story, right?
Absolutely. The weak force has played a key role in shaping the universe from its earliest moments to the present day.
Right.
And there are still many mysteries to unravel.
Well, it sounds like we have a lot more to explore. Join us after the break as we delve deeper into the weak force's influence on the evolution of the universe, the creation of the elements, and the ongoing quest to unravel its remaining secrets.